Hello, welcome to the last day of this year's Balkan. We will start with RISC and Open CPU instruction set by Lazar Stricevic. Yes.
Hello everyone. First to introduce myself, I'm Lazar Stricevic, it says on the screen. I work as a lecturer at the Faculty of Technical Sciences here at the University of Novi Sad. And today will be helping me Lazar Đurović, a student who is about to arrive with his mom soon, I hope. Anyway, how many of you have ever heard of RISC V? Oh, so a lot of people. Good, because I thought it would be a sort of introductory talk, but okay, so we could move on to some more advanced things if you would like that, I suppose. First of all, it says RISC V open instruction set architecture. What is instruction set architecture? Well, it's sort of it's a set of instructions, right, which executes, which are executed by the CPU. It's basically the place where the software meets the hardware. So CPU gets machine code instructions, and it executes them. And you get these machine code instructions by the way of compiling, or some people might want to program machine code themselves. I wouldn't do that. How are you? So why is ISA important? Well, is it? I mean, people are programming in higher level languages. Why should machine code be important? Well, if you notice that 99% of desktop and servers and laptops are based on Intel x86 ISA. Mobile devices are based on ARM ISA, 99%, and 100% of mainframes are based on the IBM System 360 ISA. So why they don't mix? Why doesn't Intel make mobile devices? Well, they tried, but it's hard for them because to enter this new market for them, right? Also, why doesn't ARM make servers? Well, they tried. Well, why there are no ARM servers? There are, but they're not so successful. It's hard to get into this market. So, as you see, ISA can be really important, and it is. Well, how come this ISA is important? How does it all work? Well, it all comes to CPU design. The main two parts of CPU design are data path and control part of the CPU. Data path is the muscle, the brawn of the CPU. And control part is the brain, which controls what the data path is doing. In the beginning, biggest challenge for the designers of the of control circuitry was to get it right, and because at the time logic was very, very expensive in comparison to ROM. It was in the age of vacuum tubes and mercury delay lines was RAM. So logic was expensive, ROM was expensive and slow, and ROM was cheap and fast. So the answer to that was microprogramming, and which basically introduced a concept where instructions were actually a way to access the code in ROM, which was then named microcode. So in this way, we got complex instructions where one instruction actually caused execution of microcode program inside ROM. In this way, ROM got to be used more efficiently. So what exactly is RISC? As you can see, this sort of a way of microprogramming created so-called complex instructions which can do many things because it was used to call basically a microprogram from the ROM memory. The instructions get more and more complex even into the age of the solid-state device. For example, VAX had an instruction was called poly, which was used to calculate the value of a polynomial in a single point. So, which was sort of strange for instruction to be used in that way, but it went up to that level. So when the microprocessor came, they kept the logic of the mini computers from previous era. So complex instructions were the main thing, but the thing is, these complex instructions take a lot of time to execute, and they are fairly unpleasant for modern parallelization techniques like pipelining. So in the early 80s, IBM developed a system called IBM 801, John Cock at the IBM, which was later evolved into IBM Power series. Before that, start of the simplification of instructions in order to execute them more rapidly was at this CDC young engineer at the time, Seymour Cray, designed CDC 6600, which was one of the first supercomputers at the time. Later, after the IBM at Berkeley, RISC processor was designed first as an academic example, followed by Stanford MIPS, then ARM, HPPA RISC, which were all made in this new RISC fashion. So what is RISC? It's a sort of it's a type of the instruction set architecture, and it's named after Berkeley RISC because Berkeley RISC was the first public specification of such a processor, which was published publicly. Typically, RISC has a small number of clocks per instruction, and it has special instructions for load and store for memory. It's called load and store architecture. Of course, once the RISC was coined, RISC became opposite of CISC. RISC, if it is reduced instruction set computer, then CISC is complex instruction set computer. So Today, CISC ISA are more expressive, more like higher-level languages because they can afford to be, which causes programs to be denser. RISC ISA, on the other hand, maps well to the high-performance pipelines and other techniques of parallelizing execution. Of course, CISC instructions can be translated into sort of RISC micro operations. But in the past 30 years or so or more, all of the ISAs that have been designed were actually RISC ISAs. So this is RISC, and now about a word or two about the open standards. In most of the computer field, we have some sort of open standards. When it comes to software, we have operating systems like POSIX standard. We have high-level languages, databases, graphic languages, network. We have Internet network, TCP/IP networks. But for the ISA, we have the rule of the two main ISA families, which are x86, Intel x86, and ARM. Both of which are very expensive if you try to use it. Anyone here tried to design their own processor? No? Well, if you try, you can invent something on your own, which can be really tricky, or try to use one of those two. x86 is virtually impossible to get license from Intel or AMD, and ARM license is very, very expensive, both for the ISA or for the IP cores. So what we need is an open, what is required is an open standard ISA, so which could be used not only on virtual machines, it could be, should be used on the real native hardware, which should work well with existing software infrastructure like programming languages, operating systems, and stuff like that. It should suit all CPU sizes, from the IoT application to the supercomputers and GPUs. It should suit most or all implementation technologies, and should be efficient for all microarchitectures. And it should support all sort of specializations, like specific type of chips, like GPUs, DLA, deep learning accelerators, and all the other types of accelerators. There have been attempts in the past, like Spark, made by Sun. Everybody here remembers Sun Microsystems. They have tried to make their CPU architecture open. In fact, they made it into a standard in 1984, but in 2010 Oracle bought Sun, and basically that is the end of Spark development, as far as I know. They have been attempting early 2000 with the Open RISC. It was a new CPU design based on the DLX architecture from the book Computer Architecture Quantitative Approach by John Hennessy and Dave Patterson. But it did suffer from many shortcomings, and did not really manage to take off. So people at Berkeley who originally designed RISC, Berkeley RISC, together with some younger forces, have decided to make yet another generation of RISC which would fit into all these requirements. Actually, not at first. First, they just try to develop something that will be suitable for classes at the university. But neither architecture at the market is suitable for that. So they have tried to design their own. It started as a 3-month project, and people started using that outside of the US Berkeley, the UC Berkeley, and they were really amazed when people started when it changed something in the instruction set, and people and got emails from people. So what are you doing? Why are you changing this? We started using it. Okay, so. They started making it into real standard, and first public RISC V specification has been published in 2011. So these are the generations of RISC, of Berkeley RISC. So far, this is the latest one. Oh, actually, it's the first RISC V tape out. Why is this important? Why is RISC V important? Well, because it is simple enough and small enough to be presented, for example, in classes, and it is simpler and smaller than any other commercial ISA. It's a clean slate design, so it doesn't have the burden of some sort of legacy architecture which it needs to be compatible with, and it clearly separates between privileged and user mode. It is modular and extensible because it has one basic ISA, standard basic ISA, and for all the other purposes it has extensions. What is important is that this basic ISA and the extensions are frozen. They cannot change. Once they are published, they cannot change. So there are no it is guaranteed that if a CPU if you write a program for a current CPU, it will work in CPU in future. This is the timeline from 2011 up to 2016. These are all academic cores, and this is RISC V instruction set. It's called the green card. It's a reference to the IBM 360 green card, which was then popular in the late 60s for the IBM 360 computer family. And this is it. These are all instructions. Actually, the basic instructions are the basic set is just this, and these are extensions. Extensions for multiplication and division, multiply, divide, atomic instructions, and for a floating point, and these are for I don't see. Okay, and these are for compressed instruction set. So these are basically the families. There are 3 basic families, actually 4. 32-bit, 64-bit, and 128-bit family, both of which work both of which all of which are frozen, and less than 50 instructions. Actually, I think it's 47 in the basic set. So, and they're all in fixed 32-bit format, except for the compressed instruction set, which are made to make better use of RAM and uses 16-bit instructions. Besides, it has a 31 register. There are two versions of 32-bit architecture, embedded and so-called normal. RV32I means integer, and all the other letters are actually marks of the extension that particular CPU supports. So ISA is open, you can use it, but there are also cores, IP cores, which you can use. They are open source. There are two main core families which are open. First one is Rocket. This is Rocket chip core. This is 32 or 60-bit single issue core. It is comparable to the ARM M series, microcontroller series, because it is in order. And of course they are out of order cores, means which are 64-bit dual and quad issue, which are comparable to the ARM A family cores. Of course, there are many other cores which are used in classes, and these cores are implemented in a specially designed hardware design language called Chisel. Chisel is short for constructing hardware in a Scala embedded language, which was also designed at the Berkeley University. So why they chose to do their own language? Well, it allows you to generate Verilog files for ASIC, for FPGA, and C++ code for simulator, which can be useful. Of course, there are many cores designed outside of Berkeley. These are just some of them, which are ETH Zurich, University of Bologna designed their own. RISC V is accepted as a standard ISA in India. Actually, India is really keen to have their own complete architecture covered, so they have adopted it as their standard ISA, and they have given funding for the several institutions to build their own cores, which would then be used in Indian industry. So one of them is Shakti, and is really already finished, and I think they started production of it. There are several other projects. Low Risk project in Cambridge. One of the co-founders of the Raspberry Pi project is also funded this Low Risk project, which probably means that RISC V is going to find its way into some new version of Raspberry Pi. We'll see. And many others. Of course, there are many commercial already cores. Most of them were designed by C5. C5 is a company founded by the guys who designed RISC V, and they have cores which you can use to build your own CPU. So what is the difference between open source and these IP cores? Well, these IP cores are closed source for a specific reason, because fabs or manufacturers of chip manufacturers actually have their own secret sauce, which is necessary for them to produce in the fabrication process. So they need to make closed source cores in order to be able to directly produce them in the factory. So basically, you can just select cores which you want to use, pay a certain amount of money, which is far less than you would pay for ARM core, and you can your own processor. For example, these are I think about $100,000. These cores, and ARM core I think you need to pay per specimen. I'm not sure, but this allows people to build their own processors, just like ordering pizza, more or less. What is significant also that NVIDIA has selected RISC V for use. For example, they have front-end controller at their GPUs and Integra SoC lines. If anyone has heard about Falcon chip, is a microcontroller which receives commands from the operating system. Well, actually, this one should be based on RISC V really soon. Western Digital for their storage devices have also designed microcontroller based on RISC V. And there are many others. NVIDIA and Western Digital are currently the biggest. I would say that ARM is particularly not happy about this. They have launched several smear campaigns to try to discredit RISC V, but so far they haven't been successful with that. Anyway, these are the cores that C5 is currently offering. These E series are based on this rocket chip, basically rocket chip with some secret sauce, which enables production, and U54 is based on the Boom core. So E-cores are all in order, have a small cache, but they are mostly meant to be microcontrollers, and U core is meant to be executing the operating system like Linux or something else. We'll see. So there are several SoC families based on these cores, because today people are not interested in single processors, less and less. Main market is for the SoC, system on chip, right? So system on chip based on the E-core is called Freedom Everywhere, and based on U-chip is called Freedom Unleashed. This is Freedom Everywhere FE 310. It is made in 180 nanometer technology by TSMC, so it is production chip. it goes, the frequency goes up to 320 megahertz, and it is meant to be mostly IoT controller. It has a whole range of peripherals already integrated, because it is meant for it to be IoT device. So here is FE310 in comparison to some other SoCs like Arduino based Atmega 28P, which runs on 16 megahertz. Well, it's not wonder, because that FE310 wins the speed contest, but it also wins the efficiency contest. So Kira boards based on this FE310. In fact, I have one here. I don't know if we can see it. Okay. It's basically Arduino. It's basically Arduino board, but it's based on RISC V. It is completely compatible with Arduino, and I would like to thank Maker Association for Noisat for letting me show this on my presentation. Thanks. Besides Hi-Fi 1, which I just showed, there are several others. Among them, Arduino Cinque, which is not out yet. I'm told, because some problems that they have at Arduino. I don't know who is going to buy them or not. But what does Hi-Fi do besides being Arduino compatible? Well, it has large number of pins, but it has a slightly larger flash memory, and it is, as I said, a lot faster. It is the fastest Arduino in the world, as I'm told, which can be seen from the comparison chart. Here it is compared to Arduino 101, Arduino 0, Arduino Uno, based on Intel Kiri Admiral 32HP. Here SoC U54 FU540 is based on the U core, and is capable of running Linux. It is the only core. It is the only physical CPU based on RISC V technology which is able to run Linux, and it is the fastest one. It has 4 cores which are meant for execution. 1 core which is made for power management and stuff like that. it has gigabit Ethernet and it is made in 28 nanometer technology also by TSMC, so it is available. So they have made a test board, Hi5 Unleashed. I don't have it here because this board is much more expensive. One costs about $1,000, I think, at the moment, because it is one of the few specimens who can run Linux. It has 32 megabyte SPI flash on board, plus micro SD card, and an expansion connector, which can connect it to expansion board, which is basically a main board for this for the computer. This configuration was used at the FOSDEM this year to play to demonstrate Quake on it. They have run Linux successfully and run Quake on it. Most of the other software runs on this platform. Actually, Linux from version 4.15 has mainline support for RISC V. Fedora 29 has support for RISC V. Debian has about 80% of packages translated. BSD, FreeBSD is translated. Zephyr operating system. Thank you. Compilers like GCC, LLVM, and all the other tool chains are also available. Simulators. And for Hi5 1, there is support for the Arduino IDE and beside that they have their own SDK, and RISC V is also described by the latest editions of the famous titles: Computer Organization and Design and Computer Architecture Quantitative Approach, which is not expected because the authors of these books are also the authors of RISC V. Right now, I would give a stage to my colleague, a student, Lazar Stricevic, who has made a simulation of RISC V. He was able to do that even though he's just a high school student. So, give him a round of applause, please.
Thank you. As Professor said, I'm a high school student and I got interested in CPUs when I was like 14, and I started like building some custom CPUs, and it was all very amateur, and I didn't know in which direction to go. So the biggest help that I could get was in applied physics and electronics course here in my high school, and also in Petnica research station. And I also had some subjects in school which were about computer architecture. And also, when I moved here to Novi Sad, I went to like Hackerspace Tilda Center. There is a big open source community, and I talked to people about how I'm interested in CPUs. And someone told me you should take a look at RISC V. And I read some things. I read like datasheet, and I was not so impressed, and I didn't understand the importance of it. So in Maker, Serbia, a man told me you should go to see Professor Stricevic, He's interested in RISC V and he can maybe help you with your project. And I went to professor, we talked a bit, he checked out my code, and he said, you know, you shouldn't do this like you've done, maybe you should check this website or this book. So my reference is this book, which professor talked about. So I'm using VHDL, and it's a harder description language, and it's not like programming language. You describe how electronics inside of FPGA will be connected, and I divided my CPU into smaller modules, which are all described in this book, and I divided it so I can make a module and then make a test bench for it, and if it passes, it's good. If it doesn't pass, it's not. So this simplified the development. So development is still in progress, and my goal is to be RV32I compatible, so it means I can run all the integer instructions which professor talked about. And for now I have only 7 instructions, but those 7 instructions represent all the instruction types. I have register to register, immediate, store, and branch instructions. And for now it runs on 100 megahertz. Also, the project is very small itself. It's got like 600 lines of code, and it's meant to be easy to understand, and for students, high school or maybe even elementary school students to understand. So now maybe we should go to demonstration. Here is the waveform, like how my signals change in time, and here this is this is program counter, so it starts from 0, and it increments by 4 because every instruction is 4 bytes in size. And as you can see, here are the inputs of the arithmetic and logic unit, and this program it adds 3 and 3. And also you can see that here the output is a bit delayed. So it happens because when you are, for example, here, everything is synchronized on the rising edge. So here you get information from the clock cycle before, and that's why this output is a bit delayed. Also, down here you can see all the control signals, which tell us how the ALU and the other parts should behave. It's like branch flag, memory read, also memory to register, and these two here down here are for ALU source. So it tells if we should get the parameter from the register, or it will be immediate field in the instruction. And the last one is ALU operation, which just tells the ALU which operation to do. And so that's the end of the demonstration.
Thank you. So now I think we're ready for your questions, if there are any. Are there any questions?
Hello. I have a question for your assistant. Did you try running these instructions on an FPGA chip?
No, currently just a simulation, but I'm working on it.
Okay, if you need FPGA chips from the Faculty of Technical Sciences, you can contact the professor or me. We can find you some.
Thank you.
More questions?
It's for your student again. So I know that you kind of built that a CPU, and I'm wondering if that's the simulation.
No, the CPU I showed last year was my custom CPU, and it doesn't have any special architecture. This is the continuation of my work on CPUs.
Nice work.
Any more questions? Thank you very much.